Hello everyone, my name is Yahya Khalid. My group mate is named Muhammad Awad, and we will be discussing our paper about um Rubik's Cube and implementing graph theory into it. Rubik's Cube is a puzzle that came out in the 1980s, and it's a 3 by 3 by 3 puzzle. And this puzzle is actually really interesting. Um, it is a puzzle that could be just solved randomly, or you can use an algorithm or math to solve it. And this actually happened. There are many algorithms out there that you can just put your Rubik's Cube on and they'll solve it automatically for you and within like 20 moves. But we decided it would be interesting to look at it in a different way and maybe develop a method through graph theory, because most mathematicians who have developed a method or an algorithm use it through group theory, which makes sense because group theory is much more practical for it. And the way that they even came up with the upper bound of Rubik's Cube was using group theory. But we felt that it would be nice to have a graph theory approach where we constructed a theoretical graph, and on that graph decided what method we would use to solve it. And the reason our graph is theoretical is because a Rubik's Cube has 6 different faces, and each face has 3 possible moves, whether it's a 90 degrees clockwise, 180 degrees clockwise, or 90 degrees anti-clockwise. And the reason that the Rubik's Cube has so many possible moves or positions is because you need to construct the number of possible positions as well as the number of possible edges and moves. And given that we have 6 faces and 3 possible moves, this gives us 18 different positions that are 1 move away from a solved Rubik's Cube. And the way we construct our graph is we start with our solved cube, and then we construct 18 different operations, which are the 18 unique moves we can do. And we each move constitutes an edge in our graph, and each new position constitutes a new vertex, which means that our graph will start off with the root vertex, and then it will have 18 different edges that connect to 18 different positions. Each edge is a different move, and if 2 vertices are connected with an edge, this means that these 2 vertices are 1 move away from each other. And the graph follows this pattern where every edge gets 18 different vertices, and because edges can only have 18 different vertices, all our edges that are in the first level will have 15 because they will be connecting to the mother root, and the face cannot be changed again. And all of their 15 vertices that are their leaves will have another 15, and so on until we've exhausted all possible positions of the Rubik's Cube. Now, this will go on for 20 moves because Rubik's Cube has a God number, which is its upper bound, and that upper bound is 20. And the reason where it will not go above 20 is because any Rubik's Cube is solvable within 20 moves. This is the upper bound, this is the number needed to solve any Rubik's Cube. If you were to randomly scramble a Rubik's Cube, no matter how many times you do it, there will never be a scramble that is not solvable within 20 moves. Now, our methodology for solving this is we start off from our solved Rubik's Cube, and we get a random scrambled Rubik's Cube, and we start off on the other edge, and we do our theory of doing 1 move away and then a different move and then a different move. And since our God's number is 20, we know that the longest path in this tree is 20. So we do this from our Rubik's Cube for 10 moves, and then we do it from the scrambled Rubik's Cube for another 10 moves. And after doing it from both sides in both directions, we now know that we've exhausted all the possible moves, and that the Rubik's Cube trees will both connect, and we will find the path from our scrambled Rubik's Cube to our root solved Rubik's Cube that is within the number of 20. This method, although might not be optimal in time or possible by a human being, it is optimal in moves, and it ensures that the Rubik's Cube is solved within 20 moves, and it ensures that it's solved using graph theory. We actually use the BFS algorithm to do this, because the BFS algorithm is able to quickly exhaust all these moves and do them together. BFS is very useful to do this, and it actually is able to do it and implement graph theory. And although we have not done the algorithm or the code, this paper could be used to fully develop a BFS algorithm that uses this methodology of graph theory to solve a Rubik's Cube within 20 moves.